Hello and welcome to our webinar today presented by Dlubal Software. Today we will be working in our finite element analysis and design software, RFEM. The title for today's webinar is NDS-2015 Timber and CLT Design in RFEM. My name is Amy Heilig. I'll be your presenter today. I'm the CEO of the U.S. office located in Philadelphia, Pennsylvania. My colleague Gerhard Riem will be your moderator, answering any questions that you might have, and he's located in our Tiefenbach, Germany office. You can go ahead and show or hide this control panel that popped up when you did log into the webinar today if it does seem to get in your way of viewing the presentation. We want to encourage everyone to ask questions, and you can also use the same dialog box in the questions section. If by chance we don't get to all of them, I will certainly send you a follow-up email. So with that said, I'm actually just going to go ahead and jump right into RFEM. I'm going to use the PowerPoint concurrently with RFEM because I really want you to know how to apply some of the theories in the program as we model. So when you launch RFEM, this is the dialog box that you'll receive, and you just simply need to go ahead and give your model a name and define the type of model, 3D, with the orientation of the z-axis upward. For our load combinations, we actually have in here ASCE 7 for 2010, the NDS wood load combinations. I check the checkbox to create these automatically, then we simply click OK. So some of you are familiar with RFEM, but for those of you who aren't, this essentially is the program. We have the tables for data input as well as our results down here at the bottom. We have our project navigator over here on the left. The project navigator can also be used for data input. We have our display tab down here. This is basically what controls everything in our view window here. We have views, which we'll be using today, and then once we run our results, we should get another tab down here that says results. And then, of course, we have all of our toolbars at the top for our modeling purposes as well. So we want to begin today with our walls, and typically with walls we would want to go ahead and model them in this vertical direction. What I find actually easiest is to use line elements to begin with, and up here we just go ahead and choose new line in the toolbar, and you'll hear me say this quite often. We have a lot of AutoCAD-like features, which I think is one of the more powerful capabilities in RFEM. So not a lot of time will be spent, trying to create very complex geometries because we have all these capabilities within the program itself, such as splines, polylines, arcs. So you can see for line options, we don't have the typical straight line, but we can, of course, choose any one of these. For our application, we'll just go ahead with a single straight line. Now all I'm doing is just using my drawing grid to draw a 40 by 20 outline of my building here, and you'll notice that I just snapped to the different points, and I'm going to add an intermediate wall, maybe right here at 12 and one more at 20. So we have nothing more than just these 1D line elements here, and what I can do is I can just select them, and I can right click, and under line I can go ahead and extrude the line into the surface. Something to note here, these are going to be cross-laminated timber panels. So cross-laminated timber is not available in RFEM. In order to define all of those different layers and properties, we have to use our RF-LAMINATE module, which we'll be spending some time in a little bit later today. So it's worth noting that the material here for our panels doesn't matter. We can just go ahead and choose something very general such as concrete or steel, because all of this is going to be overwritten later by the add-on module RF-LAMINATE. So for now, concrete is fine. I want a height of 10 feet. The thickness doesn't matter either. That will be overwritten as well. So I hit apply, and now we can see that our walls are quickly generated. Maybe we want to add some openings in these walls, and for this I'm going to go ahead and change my work plane, And you'll notice that that work plane is just on this front wall of this structure. Work planes are important because when we go ahead and continue modeling here, the work plane really confines where you're exactly drawing your elements. So I don't have to worry about drawing clear out in space, or maybe I'm accidentally drawing on this back wall. I'm going to be drawing where this work plane is set. So as far as openings, our other toolbar up here has all the different openings. And again, you know, we have just the typical rectangular opening, but we have all of these other options. So this can be super powerful when you're doing finite element modeling, or maybe you have a structure with some, you know, odd geometry for different openings in a slab or a wall. You can see here ellipses, polygons, anything that you really can think of. For us, we'll go ahead and stick with a rectangular opening, and basically I'm just going to draw some windows here, nothing too complex. Maybe we want to draw a door opening here, and lastly a window over here. Now, as far as the windows for the back wall, I can just go ahead and hold down my control key to select these openings. I'm going to use my move tool, and I'm going to create one copy and move it back 20 feet in the Y direction. You'll notice I'm kind of going through modeling maybe a little bit quick. We have plenty of other webinars that have more basic modeling. I really want to get to the CLT and timber design, so that's why it may seem a little bit quick in terms of all of the modeling behavior. Okay, so now that we have this defined, I'm going to go ahead and change my line grid now for my floors. And I just simply change the work plane again, and you'll see how quickly I can define my different origins, and now I'm at the top of the structure. We have this other button up here, and what this does is I can go ahead and select all of the model. Now, instead of a single continuous line that previously existed up here, these are now broken up where the wall panels intersect. And the reason for that is now I can go ahead and create a surface by selecting my boundary lines. Again, the material doesn't matter and the thickness doesn't matter. This is CLT that will go ahead and override at a later point. So now all I need to do for my floor elements is select my boundary lines and then do so for the second diaphragm. And we have our first floor. Now we want to go ahead and create our second floor. Well, that's just as simple as selecting our walls, and I was careful not to select the floor panels. I hold down my control key and I just drag and drop. So dragging and dropping, a very useful feature in the program, again, to really save on some time for modeling. Maybe I don't want this opening up here at the top. I can just go ahead and select it and delete it. Now we want to create a pitch in the roof. So for this, I'm going to go ahead and turn my rendering off to only a wireframe model. This way I can go ahead and select all of these lines at the roof level, go ahead and right click. I'm going to go and divide the line by n intermediate nodes, and I'm going to place one intermediate node at all of these lines. So pretty simple. Now what I want to do is I want to go ahead and highlight only these nodes, and I will go ahead and use our move and copy tool. This time, instead of creating a copy, I'm going to move these particular nodes right here in the positive Z direction 3 feet. So now you'll see that we now have a pitch in the roof. Fairly straightforward. So what we want to do now is to go ahead and draw our timber members. We go ahead and click on New Single Member here, and you'll see that the member type is considered a beam. Several other options here, but for this type of application, we just want a typical beam member. We want to create a new cross-section, and up pops our cross-section library. For this, I want to choose standardized timber. Then this dialog box will pop up for all of the different standardized timber sections. We can further filter according to AWC. We also have CSA in here, depending on which type you're exactly looking for. You can also go ahead and choose a favorites group, and I created this favorites group USA, and basically I just added in a couple shapes that I'm using for today's webinar. So rather than sifting through all of those different shapes, you can create as many favorite groups as you like and add or delete any of these shapes here. Concrete won't suffice for this timber member, so we need to go ahead and define our timber material. For this, I go into my material catalog. Of course, we want the timber filter initially, and then you'll notice that we have all of these further filters. For our application today, we want to be in North America because North America contains the AWC materials and the CSA materials. Even for AWC, it's quite an extensive list. You do have the option to search here. Again, though, I added it to my favorites group. So for this particular member, I'll use a 24F17E for my material. All of the material properties are shown right here, so very easy to access. Now it looks like we have something more like a timber material. I can click on this info about cross-section. I can get all my cross-sectional properties just at the click of a button. Now, one thing to note here, if I go ahead and click on my edit material again, and I look at my particular material model, this list isn't really as extensive because I only have a 1D element chosen right here, but I'm going to jump back to the PowerPoint. All material models are listed here available in RFEM, and technically timber is considered viscoelastic, meaning that the strain rate is dependent on time. But realistically, we can't model viscoelastic in software. It's just very complex. So we will just go ahead and consider it elastic. This is basic behavior of modeling of timber. However, I want to differentiate the different material models for our different elements. So for 1D member types, such as we're modeling right now, we'll use isotropic linear elastic. For 2D surface elements, we're using orthotropic elastic 2D. Most of us know what orthotropic is. It's just where our material properties are different in the X versus the Y direction for each surface element. And lastly, we have the solid model, and for that same concept, except for now we have 3 directions for a solid. Okay, back in RFEM, if I go ahead and click OK, and you've used RFEM before to model timber, you'll notice this error message that pops up every time. And this error message is saying you must have incorrectly defined your material. Poisson's ratio is greater than 0.5. The calculation is possible, but only E and G are applied. Is this okay? So I really want to explain what's going on here, because some of us may just click yes and not really know the logic behind why this program's throwing up the error. So timber is actually anisotropic. The properties are changing with the direction along the object. This is pretty apparent for timber. However, in the program for 1D members, we only have the option for isotropic, and isotropic materials use this equation to calculate the Poisson's ratio. It's modulus of elasticity over 2 times the shear modulus minus 1. So all the program knows is to take E and G, relate it to this equation, and go ahead and calculate Poisson's ratio. Well, 7.0 is extremely high, so that's why the program's flagging it. And it tells us only E and G will be applied. Is this okay? And the answer is yes, this is fine. And the reason why is because if we look at the stiffness matrix for a 1D member, Poisson's ratio is irrelevant. You won't see Poisson's ratio referred to anywhere within this stiffness matrix. So the fact that only E and G are applied, which obviously is present throughout this matrix, that's fine. Not using Poisson's ratio is not a big deal. For orthotropic elastic materials for 2D surfaces, it's slightly different. For the modulus of elasticity and shear modulus, they are related just basically with these equations listed here. Nothing too complex. Now, E, G, and Poisson's ratio are fully independent, unlike isotropic. So Back a couple slides when I showed you this equation E over 2G minus 1, well, this is actually not applicable for orthotropic 2D surfaces. We do have a relationship with Poisson's ratio and the modulus of elasticity, and there are equations to approximate Poisson's ratio, but again, maybe timber that's cut down on the East Coast and the exact same species on the West Coast will have a different Poisson's ratio. So there's really no way to get that exact number. So therefore, it's common practice just to use Poisson's ratio equal to 0. The program is set up to default to 0, so that's why we use 0. Looking at orthotropic 3D solids, same exact concept, except we're now adding in a third dimension. Same equations that relate E and G. You'll notice our Poisson's ratio is still 0. And then I wanted to quickly show the relationship of shear modulus for something like a solid. GXY and GXZ, these are equal. This makes sense. They're running parallel to the grain. No matter which way I flip this member, I should have the same shear modulus. But when we're looking at perpendicular to the grain, it also makes sense that we should have less of a shear modulus for this GYZ, which is how this equation relates the three. Okay, so jumping back into RFEM, here's this error. We can go ahead and click yes. So that's kind of where that's coming from, and then I can click OK again. Something to also note, we want to go ahead and apply some member hinges to this end. I want to go ahead and create a new member hinge, and the default here is to go ahead and create a pinned release to go ahead and release rotation in the local Y and Z axes. There's a nice picture here if you don't understand exactly how the local axes are laid out. Also, you have the ability to really get into nonlinearities if you choose, such as partial activity. You can define your own diagram, plastic hinges, but you'll notice everything is pretty well hidden if you just want to keep it as a typical pinned or fixed release. So these nonlinearities are possible, but yet it's not overwhelming that you have to sift through all this information just to get your typical release here. So for the member start and member end, I'll use a pinned release. And here I'm just going to go ahead and model this member between each of the walls. And the reason why I'm doing it between each of the walls, I want the pinned connection at each wall. I can go ahead and choose the rendered view again, and we can see how that timber member is applied to the roof. Now, the next thing that we want to do is to go ahead and draw in our rafters, and we'll go ahead and create a new member again with a new cross section, this time a parametric timber, and all I need to do is to type in 4x8. Now, I don't want this same material. I'll go ahead in my material library. Under my favorites group, I already have Douglas fir larch put in there. I click OK. I click OK again. Now to address the member hinges. I think where the first rafter joins this larger ridge member, I want a typical pinned release. That's fine. However, for the member end, where we're framing into this CLT wall, I'm going to define a scissor release. And what exactly is a scissor release? Well, a scissor release is where we have 4 members framing in together here at this single node. However, the continuous members, such as 1 and 2, will go ahead and transfer moment between each other. Same with 3 and 4, but we don't want to transfer moment to the perpendicular member. We only want to transfer axial and shear forces. So I think that this is best illustrated, and by the way, this was just taken from our manual. This is best illustrated with a beam or our rafter passing through the wall. You can see that moments will certainly be transferred for the items considered individually, but considered together, we don't want to transfer a moment to each other. So we will go ahead and go back into the program, and under the member hinge, we'll create a new member hinge. And here, instead of the local X, Y, and Z axes, I'm going to create a global X, Y, and Z. Then you'll notice that this option pops up here for a special type of hinge. And with this, I can now go ahead and check this checkbox for special and release all rotations. If I click OK, you'll notice that the program denotes this as a little bit different from a typical release by putting an S on it for special. So I click OK, and then I just need to go ahead and draw in my first rafter. And the other thing I'm going to do is use the drag and drop by holding down my control key to extend the member. I want to adjust my member releases here for the second one. I also want a scissor release at this location, so my member start, because I've already defined it, is available in this drop-down. Member end doesn't matter, and the reason why is because I'm going to divide this member, and I'm going to divide it by a certain distance. And you'll also notice when I'm in this divide dialog box, it's nice because I don't have to guess what's the member start and the member end. The program throws up this little black arrow here for all members showing you what's the start and the end, or the I and the J ends. So the member start, I'm going to go ahead and divide it 2 feet from the member start. I click OK, and now I have 2 separate members. And I'm just going to go ahead and delete these. So as far as the scissor hinge, I do need to move it over slightly because I'm at this intersection of 2 walls, and the program will give me an error just because it's a very odd connection to be at this particular intersection. So I'm just going to select both of them by holding down my control key. I'm going to use my move tool again, and in the X direction, 0.5 feet. Oh, sorry, let me undo that. I also had the Z direction defined as 3, so we'll change that back to 0. Okay, so as far as the rest of the members, it's easy enough as using our move and copy tool. I'm going to create 13 copies at 3 feet on center. I click OK. All the hinges, special types of hinges are there. My spacing is correct, so everything looks good. Now I need to do the exact same thing for the other side. I could go through that whole process again, or I really want to utilize the tools in RFEM. So under this Views tab down here, you'll see all of these default options. And this is basically just to select different objects in the view window here. And for example, there's an option here, members by cross-section. So all my different members by the different cross-sections would be listed here. For me, I just want to select my 4x8s. You'll notice that I can't really select anything else in the model, which is exactly what I wanted. Now I can highlight all of these, and we have the mirror tool, just like in AutoCAD. I'm going to create a copy, and it's asking me which plane do I want to mirror through. And I want to mirror through the XZ plane. And then I just simply need to choose a point at which it will be doing the mirroring. So I choose any one of these top points. I click OK. And now I have my roof. So again, a lot of features to quickly model in here. Okay, lastly for this, we want to go ahead and one more thing. Let me turn this into wire view. And if I zoom in and I just select this floor panel here and I choose visibility by selected objects, I'm really only looking at this single floor panel. Well, this floor panel is pretty long, and maybe I want to add in some type of beam along here. That's fairly enough easy to do, but I really want to drop it down so the eccentricity is included for the surface thickness as well as half the beam depth. And with that, I can go ahead and create a new member, just like what we've seen before, create a new cross-section. I'll go into standardized timber here, and I'm going to choose my other glue lam that was in my favorites list. Materials already defined, so that's perfectly okay to leave it the same as the other one. As far as my member end releases, I just want a typical pinned release. Now, there's another option here called options. Under this options tab, we have member eccentricity. If I go ahead and create a new member eccentricity, you'll see that I can either choose an eccentricity by defining the length, either at the I or the J end, or I can do a relative offset. This is really user-friendly. I want to note, though, that when you're first in this, you're trying to apply these different eccentricities. It could take a few tries before you get exactly what you want because the local axis is very important. And just because I've been in RFEM enough, I know that my local axes are opposite of what is shown here. So realistically, instead of choosing the top of the beam, I would choose the bottom here because I know my local axes in here will be modeled with the local z-axis up. Now it's asking, what do you want to offset it by? Well, I can choose either a member or a surface. So if I choose this surface and then I graphically choose this surface I have selected in here, and then again, I know my local axes are opposite here, so I actually want to select the top here. And I went ahead and click OK. Then I can go ahead and click OK again, and then now I can go ahead and model this particular beam. Now, you'll notice too that I don't need to model in extra nodes because of the CAD-like capabilities. My centerline snap point pops up, and I can choose the other center line. You'll also see a perpendicular line, so it's kind of nice in the sense that I don't really need to worry about drawing in an extra node there. I can go ahead and render it to show exactly how this beam was dropped down. You can see the rigid links that were created, and these rigid links were created based on half the depth of the beam as well as the surface thickness. So I can also go into my display down here in my project navigator, and like I said, this controls everything we're seeing here. And I can just want to show you guys that you can go ahead and render these surfaces to filled so that you can really see how this beam is dropped below that particular panel. Okay, I will go ahead and cancel my visibility mode here. And the last thing that we want to do is to go ahead and add some line supports here. Line supports can be applied, let's say, to the bottom of these walls. Default, hinged and rigid, pretty self-explanatory. If I create a new support, again, just like member end releases, you really have the ability to dive into these nonlinearities. If you have friction, if you have partial activity, if you have sliding, all of these are possible with these support reactions. So, you know, we're not going to get into this today. We'll keep it as a linear support, but just know that it is an option. So for us, we'll just keep it as a typical hinged, and we'll apply it to all the bottom of the structure. Okay, so our modeling is essentially complete for the structure. Now I want to go ahead and quickly add in some loads. For this, I'm going to go ahead and create some new load cases, and that's just opening up our load cases and combinations dialog box. So the first load combination will be dead, and we want to go ahead and keep the action category as dead, and you'll notice self-weight is activated for it. I create another one. I'll call this one live, and we'll assign it to live load. We need to pay careful attention to the action category because this is how the program assigns these load cases to the ASCE load combinations. If you incorrectly define an action category, you're going to get the wrong load factor. So keep in mind that these are important when you are assigning your load cases. We'll go ahead and assign wind here, and we'll assign it to wind. And lastly, we will assign snow to snow. Okay, so I can click OK out of here, and you'll notice that when I'm looking at my drop-down box now, which previously was empty, I now have all of my load cases, and then the program went ahead and automatically created all of my load combinations according to ASD and LRFD. For now, when you're applying loads, you want to make sure that this is set on the correct load case that you want the loads applied to. So I think what's easiest here is to go ahead and highlight our floors and make this visibility based on the selected objects. Then I can go ahead and just quickly add surface loads to my first floor. I just go to new surface load, and you'll notice here that, again, you have the options to really get into depth for your surface loads. For us, we're just going to keep it as a typical force uniform. And as I scroll through these different load directions, this little picture updates here, which is nice. So you can see exactly how you're applying it in your model. For us, we will just go ahead and stick with the ZL direction in the negative direction with our magnitude at -0.1. I click OK, and it's as easy as clicking on the surfaces. Now, for my members up at the top, I want to use our tools, generate loads from area loads on members via plane. Again, we can scroll through these different options. I'm going to stick with the typical ZL. And what this is going to do is we're going to apply an area load, and it will actually distribute the line loads based on tributary area to all the different members. Now my magnitude will be -0.05. The program's asking me, okay, well, where should I apply it? And I need to give it some surfaces here, so, or not surfaces, some area loads. I can change this back to my wireframe, and I'm going to select first the one side of the structure, and I'm going to go ahead and select the other side as well. So this will just be taken into consideration when the program is applying this dead load to the roof members. I can actually also, which I think is a nice feature, remove the influence from single members. I can remove the influence from all members parallel to a certain member. So if I choose this option, maybe I don't want the dead load applied to my ridge member. I click OK. I click OK. Up pops some math, just showing you exactly how that was applied. I can also right-click and display it separately. So without solving, I can already see what these loads are on the member, which is nice. For a little bit of a cleaner look, we can keep it as a single load. Now, quickly going through live load, same thing. We'll just apply a surface load in the ZL direction, but our magnitude will be a little bit less. And we can just go ahead and apply it to these two surfaces here. Now, wind is obviously a little bit different. We could technically do some calculations according to ASCE. And just to let you guys know, we do have the ASCE load combination generator for wind loads in our internal version now. So I'm hoping that that will be released fairly soon. For today's sake of time, I'm just going to apply a lateral surface load. I'm going to apply it in the Y direction with a magnitude of 0.03. And all I need to do is click on my surfaces. You'll notice my openings were taken into account. You know, maybe later I decide, okay, well, I don't want this opening. Well, if I delete it, the load is automatically filled in that particular opening. So everything is very automated in the program, which is nice for a lot of the changes. Now, lastly, we have snow load, and for this, I do want to utilize our load generator from snow loads for a dual pitch roof for ASCE. For this application, I think this is nice because if you're used to snow loads according to ASCE, all of these factors will look very familiar. If by chance you're not sure on a factor, if you click this info button, these are all the tables that are taken directly from the code. So it's nice that you don't necessarily have to flip to the code in order to get some of these factors. The same with the ground snow load. We actually incorporated this map here, and we can double click on, let's say, our structures in South Dakota, and it will automatically come up with our ground snow load. The roof geometry needs to be defined, and one important thing to note here, you can't just click all over to create your roof geometry. You really do need to follow these same guidelines as what this little window is showing you. So with that, I can easily just go ahead and choose my roof geometry based on my rafters here. And the program jumps back into this. Now, I'm just going to do a balanced load case, and you'll notice it automatically assigned it to our snow load. And if I go ahead and, let's see, if I go ahead and click, sorry, for some reason I must have not selected my roof area load correctly. Let's try that over again. No. Okay. Well, regardless, we can go ahead and apply the snow load here. If I go ahead and generate my loads again, I think there might have been something issue with the load combination generator in terms of my roof geometry. So for this, I can actually go ahead and select my options again, but this time I'm going to turn it into wireframe to see if that works a little bit better. Maybe I was not selecting a proper node. And okay, much better. Now I can, so that's a good point to make, that if you don't correctly define this roof geometry, this okay will be grayed out. The program's smart enough to know that, okay, something's slightly wrong, so you do need to address something in your data here. So for me, I must have clicked on a wrong node someplace. We can exclude the members parallel to member 1 again, and I click OK. Up pops my calculations for the ASCE, and then you can see here that again we can right-click and display separately, and we get a nice layout of how the load is being applied to all those different members. Okay, so now that we have all that, we can actually jump into the laminate module. So RF-LAMINATE here. I want to go back to the PowerPoint to describe what we're doing in RF-LAMINATE. So in this module, we're actually going to define the different layers of the CLT panel. Now, each layer is going to have its own properties, such as our modulus of elasticity and shear modulus. And we'll go ahead and create a stiffness matrix for each layer. Now, also in the program, it will go ahead and take each layer and then create an overall stiffness matrix. For example, this is an example from the D11 entry in the stiffness matrix based on all of the different layers. Then the program will export these correct stiffnesses back into RFEM. So we now no longer have those concrete panels and floor panels and such, but rather now we have the laminate panels with the correct stiffnesses. The program will go ahead and run all of our load combinations based on ASD or LRFD and get all of the internal forces. Then it takes those internal forces back into RF-LAMINATE. It will distribute all of the stresses to each layer based on these differential equations here. And maybe more graphically, you can see the stress distribution throughout the depth of a cross-laminated timber panel. It would look something similar to this. Then for each stress, we're actually going to go ahead and separate it into tension, compression, and bending components. Then we take those stresses and compare them to what the code's giving us for our limit stresses, and then we're going to get a code check. So essentially, that's how RF-LAMINATE is working within the program. So you can see here that I'll go ahead and go back to my rendered view, and I have a multitude of add-on modules, but I added the ones I'm in most often. You can just right-click and check favorite to move it up to the top, which is nice. So I'm launching RF-LAMINATE. When I say add-on module, this is the add-on module. It looks like another dialog box. So I don't have to remodel anything. I don't need to worry about linking data together. Everything is all within RFEM. And the other thing for these add-on modules, you just want to work from top to bottom with the input data, which is given here on the left. So just work down this list. So the first thing it's asking us is what surfaces do we want to design? I can check this checkbox all, so all surfaces are now selected in there. Now for standard, we want to choose the NDS-2015. And I want to go ahead and you'll notice we have both ASD and LRFD. I'll go with ASD. Therefore, I want to select my ASD load combinations from ASCE. So here I can just select the ASD load combinations, and these are what I'm going to use for my design. Serviceability is if you want to go ahead and do a serviceability check in the program. And under the standard, you see you can set here your limiting deflections. Today, we're not going to do this, but just to note that that is there. Material characteristics. So the first thing we want to do is to define the first composition. So here, I'm going to title this one walls. And you can, of course, go into your material library for timber, and you can add in, you know, all the different particular material types, whatever you'd like for this. Give it a thickness and a direction. But we also have this option, import layers from library. Now we're working on, so we have this list here of producers, and we're working on placing structure lambs products in here as well, so that should be available very soon. For now, we also have the 320 CLT, we have the different types here for grades, and we also have a few different thicknesses. For walls, I'll go ahead and stick with 4 1/8 inch, and now you can see that the thicknesses were automatically generated here as well as the direction of the different layers. You can see the materials listed here. I have a nice picture of how my materials are actually layered, and it's going to ask me which surfaces do I want to go ahead and define. So for this, all I need to do is just to select my walls. I click OK, and that is automatically done here. Now I'm going to create a new composition called floor. And same exact thing, we'll get this from our material library, but I'm just going to increase the thickness to 6 7/8. Okay, so the other thing to note here, if we go back to maybe our walls and we click on this button, Edit Composition Details, do we want to consider coupling, and do we want to consider that the cross-laminated timber is without glue at the narrow side? So what exactly does this mean? Back in PowerPoint, shear coupling is nothing more than are the layers glued together. So you can see here that when we do consider shear coupling, our stress diagram throughout the depth of the CLT is related. When we're not considering shear coupling, you can see that each layer kind of has its own behavior that's not related to any adjacent layer. Most likely we'll have the different layers will be glued together, so for our case we're going to consider shear coupling. Now, consideration of edge bonding, or are the boards glued at the narrow side? So this is a perfect example of where the boards are not glued at the narrow side, so therefore we'd set our stiffness in the local Y direction equal to 0. We'd also reduce our in-plane shear stiffness by 0.25. When I go back to RFEM, you can see here I'm already considering coupling. If I go ahead and check this cross-laminated timber without glue, you'll notice that my in-plane shear stiffness will now be reduced by this coefficient 0.25. That's exactly what I just mentioned in the PowerPoint. We don't have this scenario here, so we'll just leave this alone. Now for shear stiffness elements, this gets a little bit more complex. If we take a look at basically any type of rectangular section, we will always have a shear stiffness reduction, and for homogeneous rectangular sections this is set at 0.8. However, for CLT, we obviously don't have a homogeneous section. We have all these different layers, so we can't really make this assumption here. For our shear stiffness, we do need to somehow determine that, and it is the shear correction coefficient times G times A. Now, what is this K, though, for cross-laminated timber? So there are several suggestions in the several suggestions from research and such to use these ranges for 3, 5, 7, 9 layers. The question is, what if we get to a point where we have 10 layers? Or what if we really want an exact coefficient within this range, but we don't really know where exactly we fall within this range? Well, the good news is that the program does this automatically. So shear stiffness coefficient calculations according to general research and regulations, and this is also in the CLT handbook for the USA. It gives this equation for the coefficient, and it's pretty complex, as you can see. Now, when you're looking at RFEM, if we take a look at all of these insanely long calculations, this is what RF-LAMINATE is doing in the program to determine the D44 and the D55 entries in our stiffness matrix. So it's actually going through all of these calculations to get these values. Now, if you're an engineer and you have a lot of time on your hands and you're just dying to know what this coefficient is in the X and Y directions, you can actually take these values, the D44 and the D55, which we give in the program, back calculate to find out what those shear coefficient reductions actually are. So you'll notice that D44 utilizes this and D55 as well. So as I said, you can back calculate. Going back into the program, if I click on this info button here, I can open up my stiffness matrix for this particular composition, and I can see D44 here, D55. So these are the values that you would want to use. So going back to this option here, this is something that you probably won't be changing unless you really know what you're doing, because the program is automatically calculating this for you. So just keep that in mind when you're in these details options here. Okay, so another thing to keep in mind, this orthotropic direction. Orthotropic direction beta, this is the angle from the local x-axis. So we need to pay careful attention to this, and I can't stress this enough because I made this mistake preparing for the webinar as well. If we want to go ahead and orient these outer layers, because these are our strong layers. We want them to be, of course, in the vertical direction in our model. So if I click OK here, let me go ahead and go back to my floor. I forgot to assign my surfaces to my floor. And I click OK. Now, I look at my model, and you'll notice now they're blue. I double click on them. They're not concrete anymore. They're now RF laminate. In order to edit them, you need to go back into the laminate module. I can right click and I can go ahead and display my local axes. Now notice that all of my local axes are in the horizontal direction. This is not good. We want these strong layers to be oriented in the vertical direction to take those gravity loads. So I could sit here and change the orientation of all of these surfaces, but better yet, we have a quick feature in the program. If I just go ahead and select all of my wall panels, I right click and I go to Surface Edit, there's an option here called Axes. And under Axes, there is the option Axis here, and I can actually set all of my local x-axes parallel to a line that I choose in the model. And I'm just going to choose this vertical line here, and I click OK. And now you'll notice that all of my local axes are now oriented in the vertical direction. These ones come from the floor panels, so we don't need to worry about that. So again, very important detail. Otherwise, you risk, your results being inaccurate because you haven't oriented the direction of the layers correctly. Okay, so going back into RF laminate, we can continue moving down here. Actually, one more thing I also forgot to do. Along with the orientation of the axes, you'll notice here that we have our walls framing into each other, and this is a rigid connection now. For cross-laminated timber, we probably won't have a rigid connection, almost guaranteed. So how do we address that? And the answer is with line hinges in the program. So every surface is just composed of line elements on the outside. So if I go to Insert, Model Data, and Line Hinges, I can go ahead and assign a line hinge graphically. I need to go ahead and give a new definition for a line hinge. So with the screws and cross-laminated timber panels coming together, I'm probably not going to have any resistance for rotation about that joint, the local x-axis. So I'll leave this as released. Now, as far as transition along the joint, we'll probably have a little bit of slippage there, so maybe I can define a spring stiffness coefficient of 40 kips per foot squared. I go ahead and click OK. I'm actually going to use this option here that says select surfaces and automatically assign the lines. I think it's quickest. I click OK, and then here what I can do is I can just select all of my walls, and you'll notice they're all listed here. I click OK, and now I have all of my line hinges assigned. And I can see these line hinges, I can double click them, I can edit them individually. So, it's a nice feature to use that tool. However, there's one thing that we do need to clean up. Just like the example where you have two members that are framing into each other and you cannot define the member ends both as pinned. You'll get an instability. You need to have at least one rigid member and the other member framing right into it can be defined as pinned, but if you define them both, we get issues within the program. Same for wall panels. We don't want to define two wall panels framing together both with a line hinge. We actually want to delete one of those. So I'm just going to go ahead and hold down my control button, and all I need to do is just select them graphically and I click delete. Now let me go ahead and do so on the other side, again just by holding down my control button, and I can click delete. Now you might ask yourself the question, well, I see two line hinges here, but the reason why is because my floor panel is also framing in here, which doesn't have a line hinge. Therefore, we're stable for this particular intersection. The last thing that I want to do is I want to go ahead and add one more line hinge to my floor. So if I go ahead and create my visibility by selected objects, I go to my insert model data, line hinges graphically. But this time I'm going to use the same definition here. This time I'm going to select the surface and then the line. So all I need to do is select the surface first, then the line, and click OK, and then you'll notice that here I have another line hinge, and then I still have my once rigid surface framing in right here. Okay, so canceling this visibility mode, I'm going to jump back into RF-LAMINATE here, and I just continue working down my list here. Material strengths, this looks very similar to material characteristics. It's just giving you your strengths for bending, tension, and compression based on what the code is telling us. Load duration, this is just from our loads that we've already entered into RFEM, so you can see that everything's automatically linked here. Everything looks correct except for maybe wind. We want it more as 10 minutes for our load duration. Then the load combinations for ASC are automatically updated with the correct load factor. In service conditions, is your panel dry or wet? All of ours will be dry. And then you can go ahead and click on the standard button here, and we get some other factors that are applicable to our strengths, our capacities. What's nice too is that we have all the references to the code here. So you never have to guess, okay, well, I don't remember, you know, for example, where load duration comes from the code. Well, we give the reference right here. So you can flip open to the code and go ahead and take a look at that. Okay, so with that said, I would go ahead and run the calculation button now, but it takes just a minute actually, but instead I'm just going to jump to a model that's already been solved. So let me go ahead and pop open my RF-LAMINATE module. And like I said, this is the exact same model. I just have all my solution done right here. So you can see here that now my results has popped up. My max stresses are given as a ratio by loading. So we can see here that we have load combination 14, load combination 15, and so forth. Then you'll also notice that there is a stress check for every single bending, tension, compression. Every check in the code that requires shear will all be listed here. So that's one awesome thing about RFEM, is that we don't just give you the controlling ratio. We give you every single one of them. So that way, you know, you can really understand what all the different load checks are. As we scroll through these, you'll notice that our diagram is changing for all of them. But, you know, let's say, okay, well, maybe I really am only interested in the max load check. Well, I can actually just filter it according to the max here, and it jumps to the load combinations that are controlling. You'll also notice that if we go back to the full list, regardless, we get our max ratio listed right here. We have a nice green smiley face, so we're below 1.0. These other options are basically just rearranging your results. This is according to surface. So now surface number 2 is listed here. And then we have composition, so our walls and our floor that we created. We also have our material takeoff here. You know, engineers might be interested in this. for their calculations and such, to go ahead and put this report in there. So that is available in this module. Now the other thing we can do is jump to our graphics, and you'll notice that our results bar is here now, and we can actually view all of the different stresses. Although we had it in table form, maybe we want to see it, as a graphically. So we have all of our stresses here that we can view. We have composition 1, which is our walls. We can jump to composition 2, which is our floors. So, very powerful in terms of the graphics as well. And then we can even view our ratios as contour lines as well. You'll notice everything's blue because we're well below 1.0. If things were closer to failing, it would be closer to that red color. Okay, with that said now, I am going to jump into the Timber AWC module. And lucky for us, the module looks almost identical to the CLT. This is pretty much the case for all of our add-on modules. So when you're opening up, whether it's dynamics, it's steel, it's timber, all of them look very similar. So there's no need to learn all the different modules. It's going to be intuitive no matter which one you're in. You can see here that we can choose design according to ASD or LRFD. I'll go ahead and choose ASD. I have my members just checked as all now. We can also do member sets so that we create design so that all the members are maybe optimized to the same size. So quite a few options there. This is similar to what's in our steel module, to our concrete module. Now for the actual design load combinations, because I'm running ASD, I want to choose my ASD load combinations for my design. Serviceability, same thing as CLT. If we wanted to take a look at maybe some, some deflections, I guess it's not in there. If we want to take a look at some of our deflection limitations, we can go ahead and choose that for serviceability as well. Fire resistance, we also have the ability to do fire resistance design. Again, you would want to choose the applicable load combinations for here, and we would get a few more options for fire resistance. Moving down the list to materials, you can see that concrete and steel are bright red. This makes sense. We can't design a concrete or a steel beam in a timber add-on module, so that's why these are not applicable. But you can see our timber materials are applicable. Laminate is not because we need to use the laminate module. Cross sections, same thing. If we had steel in here, concrete, it would be red as well. Now you can choose to optimize these members. Let's say, we're well below 1 or maybe we're above 1. We can optimize. So we get that question quite a bit, and that's certainly an option in these add-on modules. So you can optimize from the current row, which means it will choose one of the glulam Western species, or we can choose from our USA favorites list that I showed you before. Load duration. This is the same thing as CLT. You can see here that our load cases were generated. We already have the load duration factors correct in here. In service conditions, dry and wet, pretty self-explanatory here. Effective lengths. Now this is if you want to consider buckling, if we want to consider lateral torsional buckling, we need to come up with our L effective. So the default is the full member length, but if there are some connections in the program that will actually give some more, or give you a shorter unbraced length, then we can go ahead and modify that here. Additional design parameters. This is actually you can see here we have shear edge bonded factor, shear reduction factor, incising factor, repetitive factor. What's nice too is that all of the locations in the code are listed here. So again, if you're not sure what an incising factor is, well, you can just jump to the code right here. And all this is just a drop down to consider it or not, and then we will go ahead and apply that factor to our capacities. Cross-sectional area reduction. If you have a notch in the wood, we can take that into account too. This will obviously change your cross-section across the length, so we can go ahead and tell the program where it's located and the proper geometry of these cross sections. If we click standard again, this just gives us a lot more factors according to the NDS. Again, we have all of the references here, and I think that as far as our timber module, we're very strong in timber. So I think that we offer a lot more as far as the factors in comparison to maybe some other competitors. Stability coefficients for built-up columns, shear reduction factors, load sharing, everything is pretty much available here. So all I need to do is just to go ahead and click the calculation button, and you'll notice that I get my green smiley face. Again, just like CLT, I can filter if I want. Also keep in mind that throughout the program we have direct links to Excel. So you don't need to worry about copying and pasting, but we can actually use this button to directly integrate with it. We get the design according to the cross section. Maybe more interesting would be the design by the particular member. And again, so powerful in the program that we give every single check and not just the controlling ratio. And even better yet, we give every single variable that's used. We list our cross-sectional data that's being used, our internal forces that we're comparing it to. So we get very little tech support on, okay, I don't understand where these numbers came from, or, you know, maybe I don't understand why this code check is controlling over this one. Everything is listed here. So it's nice. It's very thorough. And then, of course, the takeoff ratio, parts list by members located at the end as well. We can view everything graphically. You'll notice for the NDS, we don't really have anything too much to show here other than the design ratio. But you can always switch back to one of these load cases in RFEM to show your results for, you know, let's say these different members here. We can show internal forces, which if I change this to wireframe, you'll be able to see it a little bit better. So quite a few options in terms of running a timber analysis. Okay, one quick thing before we conclude the webinar. I just want to show you guys the printout report. Again, I think it's something that is quite powerful, especially in comparison to a lot of other printout reports that you have probably dealt with other software competitors. So you'll notice that a completely separate application pops up, and it is basically, here's our table of contents right here, and let's say we want maybe cross sections before line supports. We can just drag and drop, and the program will automatically update that. But not only RFEM, we also have our add-on modules listed down here, RF-LAMINATE, you know, everything was brought in from those add-on modules as well, including some layer diagrams. You can always add pictures in here. If something were to change in your model, you don't have to worry about reprinting pictures. Everything will be updated automatically. So everything's very synchronized within the program. Okay, so that essentially concludes the webinar today, and I want to encourage everyone to visit our website at dlubal.com. If you are interested in these add-on modules that you saw today, RFEM, or anything else. We do have plenty of social media blogs. YouTube is, I think, one of the best because it has recorded webinars such as this one that you can watch for free on all of the different topics. Our email is info-us@dlubal.com, and you can also reach us via the phone at 267-702-2815. And again, this is for our Philadelphia office. We will certainly have many more upcoming webinars. In fact, we have one tomorrow for our new add-on module, RF piping. You can register for that one or any of the other ones coming up at dlubal.com under support and learning and webinars. If you are interested in PDH credit today, that's no problem. Just shoot me an email at info-us@dlubal.com, and I will be happy to send one of those back to you. And with that said, that concludes today's webinar. So I do hope you enjoyed it, and I hope to see you at the next one. Thank you.